Welcome back to segment 7. We're going to be working some problems. I know these are a little dry, but I really want to respect your time and give you the most learning I can in the time frame you have. We're on 14.3. I hope you tried this on your own. I'm going to go ahead and sketch it and then map out the next problem so you can get an idea of how sketching a curve very quickly can help give you direction. It's kind of like the mole road when we do stoichiometry. So we want to do 5 segments: up for heating a solid, over for melting a solid, up for heating a liquid, over, hopefully a little flatter this time, for vaporizing, and then up for heating a gas. Now, this flat portion here is representing my melting point. And in our question, we are told that the melting point of bromine is minus 7 degrees Celsius. We've got temperature on this and heat on this axis. And then this flat segment here, if we just extend it over just to get it to the axes, that point here that we have right here represents our boiling point. And that boiling point for bromine is 59 degrees Celsius. And the problem asks you to label the axes, including the values for the melting point and the boiling point. So let's go ahead and get units. Heat would be in joules and temperature in degrees Celsius. So this would be our solid. This is the solid end of melting. This is the liquid end. In between we have solid and liquid. This is pure liquid. This is the liquid end of vaporizing. This is the gaseous end. In between we have both liquid and gas. And then finally this would be my gas. Now if we look on, for example, 14.4, I'm going to do the work on the next page. But for 14.4, it asked us to take 125 kilograms of bromine from minus 7 up to 55 degrees. Now what's key is it told me I had liquid bromine. So on our chart we had liquid bromine at minus 7, and we're going up to 55. Which means there's no phase transition in this one. All we're going to need is MCAT to do this problem. And so let's move on to the next slide and work that problem out. But it helps to lay it out on the graph, on the curve, so that you know whether or not you're going through phase changes in addition. We've decided we're not going through a phase change, so we just need Q is equal to mass. Now remember, your mass has to be in grams. So we need to just move our decimal point over, or set up your dimensional analysis if you need to. Now, the heat capacity value is given. You don't memorize those. Even for water, I don't expect you to know that. And my temperature, my final was 55. My initial was minus 7. So it's 55 minus a negative 7. And if you work that mathematics out, it's plus 1.78 times 10 to the 6th joules. Note that the way it was worded gives us an indication that it's endothermic. Energy needed. Energy required. That means we're going to have a positive Q for our heat, which is equal to delta H if we're at constant pressure, which a typical phase change will be done at constant pressure. And we're looking at an endothermic process. Now let's try the next one. Let's go on to 14.5. In 14.5, the question asks us to determine the heat released. Now pretty soon you're going to come across some problems where all it says is the heat involved. and you're going to have to decide if it's needed or released. So let's lay it out. We've got liquid bromine, it's frozen. So all we're doing on a curve is going from a liquid to a solid. Now, if we're going to do this in the freezer, remember that would mean it's exothermic, which is in agreement with heat being released. Now, in a phase change, you have to supply the negative at the end of the mathematics. So let's work that out. I use dimensional analysis. My conversion factor is given as 10.57 kilojoules equal to 1 mole. I don't have moles, I have mass, but mass to moles should not be a problem for you. So let's set up a railroad. You can do it with the time sign. You know, I accept either way of doing dimensional analysis. So let's set that up. And I have 33.88 grams of bromine. And 1 mole, be careful here, bromine is Br2. So when we do the molar mass, we had to multiply that by 2. So we get 159.81 grams. Now I want to get rid of moles. My grams have canceled. I want to get rid of moles and go to kilojoules. And the given constant is 10.57 kilojoules for every 1 mole. Now, there's nothing in here mathematically that gives us the sign. Your knowledge of the freezing process has to provide that sign of a negative 2.241 kilojoules of energy required to freeze the liquid bromine.
Okay, now if you'll notice, I have actually skipped a problem here, and I can give you the answer to that in class if you'd like to, but it was a little repetitive. And I wanted to get into a combination question that I made up for you. So let's take a look at our graph. We would have our x-axis and our y-axis here. And I just use platinum metal. I don't know why. I thought it'd be kind of fun to use a different kind of metal. So now remember, whenever you do these, you want to completely draw out the possibilities. So I can heat a solid, I can melt a solid. Melting, remember, is that plateau. I can heat a liquid, I can vaporize a liquid, and I can heat a gas. Or I can go in the reverse. I don't have to do this up. I typically draw them up, but it's perfectly reasonable to go in reverse as well. Now remember, this is temperature and this is heat in joules. Typically, although sometimes you will see time, and that's a time that a constant heat has been applied. Now, I did notice when I wrote this problem, I did it very quickly in class today, that I missed writing a few pieces of information that we need. The melting point of platinum is 1769 degrees Celsius, and for the mass, we're going to use my birthday, 322. So 322 grams. All right, now when you approach these, you want to map out what you have, or you're going to try to do this in one step. And you're going to see this is actually a 3-step problem. And you wouldn't know that if you didn't map it out. You would attempt to just use MCAT once, and that's not going to work. So let's go ahead and put the melting point in. Remember, the melting point is the plateau. There's no change in kinetic energy and hence no change in temperature during a phase change. Everything's going into increasing potential energy. So that happens at 179, and this is degrees Celsius. The boiling point for this, way up here, this boiling point is 3827, really high up there. We're not going to get that far. So if you mapped it over here, this would be your boiling point, right? That plateau. All right, we're starting at 1500, so we are below the melting point, and we're going to end at 1900, which is below the vaporization temperature. So we have 3 segments that we're going to do. That's one segment, Q1. This is the second segment, Q2. And then this is the third segment, Q3. All right. Now, Q1, let's go ahead and start this. Q1 is taking the substance, the platinum, and going from 15, sorry about that, let me erase that, 1500 degrees Celsius to up to our melting point. So we're going 1500 up to 1769. That's a temperature change. So we're going to use MCAT there. And so Q is equal to our mass, 322. Now be careful because you're given 2 heat capacities here. We have the heat capacity for our solid, and I had to make up a heat capacity for the liquid because I couldn't find one. So we're just made up a value. That'll work for the question, okay? Just make sure that you pick the one for the solid because up to this point we have solid. And during that transition we have different states. So we're in the solid state now, 0.13. Remember, it's final minus initial, so it's 1769 minus 1500. And when I crank through that math, I get 1.126. Be very, very careful here. Times 10 to the 4th, notice on this step we get joules. All right, so I'm going to go ahead and convert it to kilojoules right away. That's 11.26 kilojoules. All right, now let's do Q2. In Q2, we're going to go from solid to liquid. In between, we have a mixture of both solid and liquid. And there's no temperature change. I can't use MCAT. Instead, we use this heat, that delta of fusion, delta H of fusion, and that's 22.17 kilojoules moles to the minus 1. Sorry, that unit ended up over there. Now, that's per mole, notice, per mole. Moles to the minus 1 is per mole. So what that's like saying is that there's 22.17 kilojoules equivalent to 1 mole. That's what per 1 mole means. So we're going to use dimensional analysis to work this step. And it's a pretty quick 2-step problem. We start with mass, 322 grams. Mass to moles, use molar mass. The molar mass is 195.08. Now I'm going to use my heat of fusion as a conversion factor. 1 mole is 22.17 kilojoules. And when I complete that calculation, I get 36.59 kilojoules. Okay, for Q2. Now, let's try Q3. So the third point is another MCAT. I'm going to take that liquid and I'm going to heat that liquid, but this time I have to use my, made up heat capacity of a liquid. So it's the same 322 grams times the heat capacity, 0.45. Now, it's my final, and my final this time we're going to end at 1900. So my final is 1900. My initial is 1769. I'm still at that temperature of my melting. And so if I crank through that math, I get 1.898 times 10 to the 4th joules, which is equal to 18.98 kilojoules. So this has shown you 3 steps here. An MCAT, then using the vaporization right there. So that's 1. These could be individual questions. That's 1. And this is 1. Now, to get my total, what I do is I add all 3 of those up in my 3-step problem. So you could have 1 step, 2 step, 3 step. honestly, you could have maximum of 5 steps. And to get the total, sorry, my Mimeo's a little jumpy tonight. To get my total, I add up each step. Heat's a state function, so I can get to it in a variety of ways. So I'm going to take, whoops, I don't know why I put kilograms there. I'm going to put my 11.26 from Q1. Then I'm going to add in my 36.59 from Q2, and then in my 18.98. And if I've done all my algebra correct, and I'm sure you'll tell me if I didn't, that 66.83 kilojoules is my final answer. All right, you will see more of me or hear more of me and see more of me in class. So until then, this is signing off.